Okay, so now we're starting chapter 7, which is quantum theory of the atom. Um, the first part of this chapter deals with 4 main equations, and we're going to learn how to solve those 4 equations. And if you know how to do that, it's, manipulate an equation properly and solve for the unknown, do the algebra correctly, pay attention to units, you'll be fine. And then the second part of this chapter deals with quantum numbers. So we'll learn about the 4 quantum numbers, and we'll learn what they mean and how to relate that to um, uh, electron configurations and orbital diagrams and things like that, which is more a topic of chapter 8. But right now, let's get started with talking about the electromagnetic spectrum by defining what a wave is. A wave is a continuously repeating change or oscillation in matter or in a physical field. What are some examples of waves? Well, light is a wave. Visible light, X-rays, radio waves, they're all forms of electromagnetic radiation. Here's actually the electromagnetic spectrum. It's in your book. And you'll see here that this spectrum contains gamma rays, X-rays, far ultraviolet, near ultraviolet, visible light, near infrared, far infrared, microwaves, radar, TV, FM, AM, radio waves, all of this good stuff, okay? So you will usually be given this on an exam if you need to look things up and tell me which part of the electromagnetic spectrum we are in, all right? So you might want to print that out and have it handy while you're doing your homework and things. Okay, now a wave, whenever we're talking about any wave, we characterize it by 2 main things: wavelength and frequency. Hold on, let me get this here. Wavelength is symbolized by lambda, Greek lambda, and frequency is the symbol of it is nu. This is the symbol for frequency. What is wavelength? Wavelength is the distance between 2 adjacent identical points. So it's a distance. Wavelength is measured in meters, in nanometers, and also in angstroms. Those are the 3 typical things you will be seeing for the units for wavelength. Frequency is the number of wavelengths, hopefully you can see this, the number of wavelengths that pass a fixed point in 1 second. So frequency, the units are per second, or second to the -1. So you'll see S to the -1, or per second as units for frequency, which is also hertz, Hz. Okay, so those are your units for wavelength and frequency. So we are going to get started with the first of the 4 equations that I need you guys to know how to work on. This first one is just the relationship between wavelength and frequency. If you take a wavelength and you multiply it by its frequency, that will equal the speed of light. So C is equal to lambda nu. That's your first one that first of the 4 that you need to know. C, which is the speed of light, is 3.00 times 10 to the 8 meters per second. So lambda would be in meters, and nu is 1/2 so that's where we get these units from. Okay, so plug and chug. If you know the speed of light, that one you should know, 3 times 10 to the 8, and I give you wavelength, you should be able to find frequency. If you know the speed of light, which you do, and I give you frequency, you should be able to find lambda. This is the first of the 4 things that we need to know. All right, so let's go ahead and do a problem here. All right, here it is. What is the wavelength of blue light with a frequency of 6.4 times 10 to the 14th second to the minus 1. Okay? I could write 6.4 times 10 to the 14 per second, or I could write 6.4 times 10 to the 14 hertz. Okay? Any one of those is the same thing. All right, so we know that C is equal to lambda nu. I have nu and I have C. I can find lambda. So lambda would be equal to speed of light divided by nu. Speed of light is 3.00 times 10 to the 8th meters per second. Nu is 6.4 times 10 to the 14th second to the minus 1. So this is per second. The seconds will cancel because this is denominator of the denominator. You cancel this. And you end up with the units of meter. Okay? So you plug it into your calculator. Anytime you have exponents in the denominator, please don't forget, just put parentheses around it so that your calculator understands what you're doing. Because a lot of people mess up, and honestly, at this level of chemistry, you shouldn't be doing those types of mistakes. But a lot of people will put it in as 3.00 times 10 to the 8th divided by 6.4 times 10 to the 14th. If you do that, it's going to think you're dividing by this and then multiplying the whole thing by 10 to the 14th, and you're going to get a wrong answer. So be really careful. Anytime you have exponents, just always put parentheses around this. Plug it into your calculator, and you're going to end up with the answer of 4.70 times 10 to the minus 7 meters. Actually, it should be 4.7 since we need only 2 sig figs here. So 4.7 times 10 to the minus 7 meters. What if they wanted the answer in nanometers? You should know how to convert to nanometers. All right, based on metric conversion. You say 1 nanometer is 10 to the minus 9 meters. Remember how I taught you how to do the metric conversion. And bring the minus 9 to the top, becomes positive 9, and minus 7 is positive 2. So it's 470 nanometers. Okay, that would be the wavelength. Okay, so that's one problem. You can do it the other way. If I give you wavelength, you should be able to find frequency. So let's go ahead and do that. Again, really easy, plug and chug. Shouldn't have any difficulty with these guys. They're not hard at all. This question says, what is the frequency? What is, I can spell is for some reason. What is the frequency of red light? This is part of the visible spectrum. Red light having a wavelength of 681 nanometers. Now notice, they've given us the wavelength in nanometers. If we're going to use that equation that says C is equal to lambda nu, we have to make sure that the wavelength is in meters. So you're going to have to convert your nanometers to meters before you plug it in. All right, so we're going to go with C is equal to lambda nu, and we're looking for nu, so nu is equal to C over lambda. C is 3.00 times 10 to the 8th meters per second. Lambda is 681 nanometers, but we better change that to meters. So 1 nanometer is 10 to the minus 9 meters. Okay, so nanometers cancel. We have 3.00 times 10 to the 8th divided by, open parentheses, 681 times 10 to the minus 9, close parentheses, press equals, and you will get 4.41 times 10 to the 14th second to the minus 1, or per second, or hertz. Okay, so that's the first equation. The second equation deals with relating this stuff to energy. And we use a constant called Planck's constant. So let's get into that one. Hold on a second. You can read the background of all of this stuff in your book, but my job right now is to show you the 4 different equations you need to know. So this next one is E is equal to H nu. E is energy. H is Planck's constant. That will be given to you. Planck's constant. And nu obviously is frequency. Okay, so what are the units that we're looking for here? Well, H is Planck's constant. Let me write it down for you guys. It's 6.63 times 10 to the minus 34 joule second. That's your Planck's constant. Just double check, it's 10 to the minus 34, not minus 33. I'm pretty sure that is correct. Yes. Okay, so Planck's constant, and then if you multiply it by 1 over second, which is the frequency, you end up with joules, which is energy. So this equation, if you know the frequency of a wave, you can figure out the energy of that wave. If you know the wavelength of the wave, you can convert wavelength to frequency and then figure out the energy of the wave. So this is your second equation you need to know. The first one was C is equal to lambda nu. The second one is E is equal to H nu. All right, so let's go ahead and solve this problem here. Blue-green light. Blue-green line of the hydrogen atom spectrum has a wavelength of 486 nanometers. What is the energy of a photon of the light? Okay, so since they're looking for energy, I'm obviously going to have to use this. They've given us wavelength. They haven't given us frequency, but using the equation from before, we know that if we're given wavelength, we can easily convert that to frequency, right? Frequency is equal to C over lambda. So I know C is 3.00 times 10 to the 8th. I know my lambda because they gave it to me. I have to make sure I convert this to what units? To meters, right? Because C is meters per second. So now plug and chug. Let's put it in. Energy is equal to let's put the Planck's constant here. 6.63 times 10 to the minus 34 joule second times, I'm going to put this instead of nu, times 3.00 times 10 to the 8th meters per second. And then I'm going to divide by 486 nanometers, but I got to convert that to meters. 1 nanometer is 10 to the minus 9 meters. Hopefully you can see all this, okay? So all I did was plug and chug. I put Planck's constant for this, and instead of nu, I put C over lambda. So now it's the matter of plugging in everything into your calculator correctly. That's the hardest part of all these, honestly. The equations themselves are pretty straightforward. You shouldn't have any difficulty with them. The only problem is that people plug things in wrong. Oh, here's another thing a lot of people forget. They forget to convert to the proper units. So if you're given nanometers, make sure you convert it to meters so you can plug everything in. Once you do the math correctly, this times this divided by all of this, put parentheses because there's an exponent here, you end up getting the value of 4.09 times 10 to the minus 19 joules. Okay, there you go. We finished 2 out of the 4 equations that you need to know for this chapter. Next video, I'll give you the other 2.